Hello everybody, and welcome to Module 9 of our course. You have somewhat made it to a monumental point. A lot of what we have been discussing we're going to finally bring together here in Module 9 as we start looking at really our first significant tests. Now, we did a Z-test earlier where we talked about significance, but this time we're going to look at three of the most common tests, all grouped together under one heading, and that is a T-test. Stands for student test, which actually goes back to Guinness and the Guinness Beer Factory, but that's for another time. So, anyway, congratulations on getting this far. So this module is going to cover the three T-tests, and we'll work on this for a while. Okay, so with that, let's begin by looking at our module goals. So first of all, we're going to describe the similarities and differences between the T-distributions and the normal curve. A lot of what we're going to hear, like I said, we've been working up to this point. So we've been talking about the normal curve quite a bit, and now we're going to look at T-distributions and see how that fits in with our concept of the normal curve. We're going to distinguish between correlated or dependent and independent T-tests. Correlated can be called dependent. They can also be called paired. But we'll see that there are correlated and independent T-test models, and we'll talk about when to use each of them. There are a total of 3. Perform the necessary procedural tasks for determining whether to use a separate variance or a pooled variance T-test model. Those fall under the independent side of it. Compute the degrees of freedom for the 3 T-test formulas discussed. Calculate t-values using an appropriate t-test model when provided data. Use the table of t-values to determine the critical value of t for the areas of rejection. Interpret a test of the null hypothesis from a t-test. And then finally discuss non-significant results in an appropriate manner. So with that, we have discussed using samples to infer information to the population. That's the whole point of what inferential statistics is about, is we have looked at our population and we're trying to infer what we believe our population parameters are from our sample statistics. So we have discussed that by using samples we know that there is error present as the samples do not match the population exactly. The larger our sample size, the smaller our error, as we have seen. Because we use the standard deviation of the sample when computing the standard error, this can be mitigated if we have several samples. But what if we only have one? What if we only have one sample from our population, and that's what we want to see is significant? The standard deviation may deviate from the population's deviation so much that we inaccurately describe what the data are actually showing. And this is quite often the case, especially in education, that we have one sample. We don't have multiple samples where we can find error and use those formula that we discussed for sample error. We typically only have one sample, and if we happen to get that one sample where our sample standard deviation deviated from the population standard deviation so much, what we end up doing is inaccurately describing what the data really show. Because we know error is present, especially in small sample sizes of n is less than 30, we cannot rely upon the normal curve in our normal distribution, or as our normal distribution will become too inaccurate. So we're really looking at smaller sample sizes of less than 30. In order to do this, we'll take a look at the t-test model, and this will fix the problem for us. we'll examine the t-test during this module and then discuss it as we move into the next module, because it will naturally flow in, though we will spend some time working on this module. So, think back to our normal curve, okay? Rather than a single curve like we have traditionally seen, the t-curve, or the t-distribution, is what it's technically called, the t-distribution, varies depending on our sample size. So we've always drawn that same normal curve and we're going to see that it doesn't quite apply all the time. The curve for the t-distribution is symmetric about the mean, just as we have always said, but the tails of the curve change according to our n and our degrees of freedom. Okay, and we've discussed degrees of freedom as well. So let me give you an example of this. So notice this curve here. Notice if we have 1 degree of freedom, well, let's start with our normal curve at the top. So our normal curve is very high in the middle, and as it comes out, it approaches the line of our curve, obviously, as we said, never touching it. If we have 20 degrees of freedom, the longer dashed lines, it's smaller in the middle, it still evolves around the mean, but as we come out, notice that the ends of our curve start to go up slightly. When we continue to decrease our degrees of freedom, with 5 degrees of freedom, we see the small dashed lines, and it's even increased, the tail has gone up at the end, and then finally 1 degree of freedom, you can see it's up at the highest at the end. So what does this mean for us? This is just an illustration, but what does this mean for us when we're looking at critical values? So the one critical value I've told you to memorize is 1.96 at the 0.05 level. So what does that mean for us then when we're talking about a t-distribution and degrees of freedom, and saying that this somewhat mirrors the normal curve, but it's not completely the same? So what we're talking about here is we're saying that the t-test has many roles in hypothesis testing. We're going to concentrate on 2 of those roles within the scope of our course. 2 sets of data, different measurements with the same scale, may be generated from the same subjects. Okay, same scaling being interval ratio, that kind of stuff. We'll see that in a minute. But we have 2 sets of data from the same subjects. Okay, for example, we might look at a group of students who have taken their SATs, and we want to compare the verbal and quantitative scores to see if there's a significant difference between these 2 scores. Okay, so we have 2 sets of data generated by the same subjects, the same students, and we have 2 sets of data from them. The other area we'll concentrate on, we have 2 different groups of students using the same set of data. For example, if we were to give a self-efficacy test to 2 groups and then expose one to treatment and not the other, then administering the self-efficacy test again to see if there was a significant difference among the groups. So you see what the 2 things here. We're going to come back to this throughout the module, but we're looking at 2 ways that we're going to concentrate on t-test. Number 1, the same group of subjects with 2 sets of data, and number 2, different groups of subjects on the same data. Okay, so we'll come back to that, but that's getting you started there, and you can see how this can apply to just about any education setting you could think of, and we'll see some more examples of that. So let's move on. Factors to consider. If we have 2 groups, for example, we have Group A and Group B. We'll just refer to Group A and Group B and Class A and Class B through most of this presentation. and we have equal number and equal standard deviations. Okay, so let's look at the groups here. Okay, we could have two situations explained in this image. So first of all, look at image A. And notice what we're saying here. We're saying the n of A equals n of B, the S of A equals S of B. But look what would happen if they had large differences within the mean. There would only be a small overlap between the two distributions. If we looked at sample B, again, the same thing. We're assuming that n is equal and S is equal, but there's a small difference between the means. Then there's a larger overlap between the two groups. So we can see the size difference we can see the size of the difference in the mean can have a large impact on determining if data sets are significantly different. Okay, if the mean difference is larger, then the less overlap. If the mean difference is smaller, then there's more overlap. So the difference in our mean of the two groups is going to have an impact on how we determine whether or not it's significant. The same thing can be said about variability. Okay, notice instead of mean, now we're looking at variability. This is our standard deviations. So in in the first illustration, we see there's a large difference within our variability and there's small overlap. In the second demonstration, similar to what we saw earlier with the mean, there's small difference in the variability, and so the chances of overlap are greater. So what does small variability in the image, why does a small variability in the image show a greater opportunity of significant difference in the two sets? And here's the answer. Less variability means the more likelihood there will be a significant difference. And finally, we've hammered home the concept of sample size. The larger our sample size is, the smaller error that we have. And we've seen that and taken some samples in the previous modules and shown that changing sample sizes has an impact on error and ultimately an impact on our final scores when we're comparing to our final scores when we're comparing to critical values. The level of confidence we can have that two sets of data are different, 95% confidence it was not by chance, etc., is directly related to the magnitude of the difference between the means and inversely related to the variability of the sample data of the groups. In other words, the greater the difference between the means and the smaller the variability, the more likely that we're going to see there's a significant difference. And that makes sense. If there was a tremendous amount of variability, when we take that variability into consideration, we see that larger overlap, and so we lose some of our value due to our lack to control that variability. So that's why the smaller variability is important. And this is basically a formula that we will see for a t-test, and those factors are in here. Okay, the t equals the mean of A minus the mean of B. So we're looking at that large difference in our means. And then on the denominator, we have the square root of the variance of A over n of A plus the variance of B over n of B. So the smaller variances and larger n's. All of these things are conceptual things, but as we work through this, we'll explain them in more detail. So, it's a little blurry, but just to give you a simple idea, when we're talking about our normal curve, we saw this before. when we're looking at, let's say, a critical value at the 0.05 level that was plus 1.96, and so anything above 1.96 we would reject our null hypothesis. With the two-tailed critical value, we saw that we spread that out over both ends of the curve. But it looks slightly different when we use the t-distribution. Okay, you don't have to memorize this. There are charts for everything, and you'll see those charts. But it looks slightly different. So let's look at the t-distribution here. Okay, notice in the top left our normal curve. There is our critical value of 1.96. This is the 0.05 level. Okay, notice that it changes though. These other three images are t-distributions. And so notice that our critical value changes from 1.96, and it depends on the degrees of freedom. The more degrees of freedom, larger samples in other words, the lower our critical value. So for example, let's start down here at the bottom. If we have degrees of freedom of 100, meaning we have a large sample size, our critical value at the 0.05 level is 1.992. Okay, it's slightly different than this. Remember, our critical values for t-distribution are going to be dependent on sample size, and which correlates to degrees of freedom. So with a degree of freedom of 100, our critical value is 1.992. But if we lower our degrees of freedom to 20, meaning we have a smaller sample size, notice our 0.05 level of significance, our critical value of t has increased from 1.992 up to 2.066. And then if we lower it even more to 10, meaning we have a very small sample, our critical value of t is now increased up to 2.228. So you can see again, it just emphasizes what we've said all along. The greater the value, or the greater our sample size, the easier it's going to be for us to make determinations of what we're doing. Okay? So that's a little bit of a conceptual idea of the t-distribution as opposed to the normal curve that we talked about. So as we go through working with t-test, we're going to see that we can't memorize our critical value at the 0.05 level of 1.96. That's a z-score. We're going to memorize that. We're going to use that a lot. But for now, as we move into t-test, know that we're not going to be using the critical value for our z-scores. We're going to be using critical values for our t-distributions. And we will be able to look at a chart and figure out how to do that. Okay? So the basic idea here, what we're going to do is we're going to calculate the t, find our t value using the formula that we will see, one of the formulas that we'll see. We'll compare our value of t with the appropriate degrees of freedom at the predetermined significance level. And remember, we've always talked about predetermined significance levels, and this typically is at the 0.05 level. If our calculated t is greater than the value, then we will reject our null hypothesis and conclude there is no difference between the two groups. Okay, so here is an example of what the t-distribution table looks like. So our critical values of t take these three things into consideration: our degrees of freedom, our significance levels, and either a one or a two-tailed test. So all of these things we've discussed in the past. We're just putting them together in this new chart called the t-distribution. And you can see across the top there are a level of significance for a one-tailed, there are a level of significance for a two-tailed, and here are our degrees of freedom. This is similar to finding critical values we've discussed in the past. If our value exceeds the critical value, there's a significance at that level, and we will say p is less than 0.05 at a 0.05 level of significance. Okay? So I said there were three types of t-tests. So you can see from this graphic we have our t-test on the left. That breaks down into what we call dependent or independent, and sometimes you'll hear the dependent called the paired or correlated t-test. And that's a test in its own. The independent test has two versions, and that's the unequal or separate variance or the equal or pooled variance. Okay, so our three types of t-tests that we're going to deal with are dependent, independent, unequal variance, and independent pooled variance. Those are the three tests that we're going to look at. And I'm going to give you examples of why we would use each test, and it all depends on our groups and the variance within our groups and the numbers within our groups and our assessments we're using. We'll pull that all together, okay? Just to remind you a little bit of numbers, really what we're looking at is interval and ratio numbers here. And there are other ways of dealing with nominal and ordinal scale numbers in testing that is out of the scope of our course. So what we are looking at, though, is differences using interval scales and ratio scales. All right, so which of the three tests do we use? And we're going to work through samples of each of these. So we're going to ask the question, are the scores for the two means from the same group of people? If we say yes, then we use a dependent t-test. And if we say no, we continue down our chart. So let's assume that we said yes. And so let's look at what a dependent t-test or a correlated or a paired t-test looks like. And what are we talking about when we say the two means from the same people? What does that mean? So let's get an example here. So in our first example here, we have a principal who wants to determine if teachers who are not trained in reading could enhance their self-efficacy at teaching reading after some targeted professional development. He provided a pretest to the students at the beginning of the PD that measured self-efficacy on one's ability to teach reading. I should say to the teachers, not the students. The principal then at the end of the PD gave the same assessment a second time. Do the two sets of values on self-efficacy ratings differ significantly? Okay, so what we have here is one sample or one group, a group of teachers, and two assessments. And we want to see if there's a significant difference. You can think of this as a pre-post test. If you're going to give a pre-post test in anything, then you would use the dependent t-test. So we will use what's called a correlated t-test because we want to examine the mean differences between two sets of data that have been collected on one group. Okay, and I'm going to show you this in an Excel sheet in a second. I want to show you the formula. From here on out, we're not going to work these out by hand, but you can see in our formula we're taking the difference in the means of the groups, and we're dividing that over the square root. Here is our variance. Here is our correlation. So this is part of the reason why this is sometimes called a correlated t-test. Because we have one group and two assessments, we want to see that correlation within those groups, and so we're going to take that into consideration. Then we're going to divide that all over in here. So with that, let's leave this and let's go to Excel and look how we can do this in Excel. That's what we're going to do from now on, is just show you how to do this in Excel. Okay, so I've input some data here, a pre-test score and a post-test score, and we want to see if there's a difference here. And after I put the data in, I thought, actually what we need to do is think of this, and this is just hypothetical in this situation, but A lower score on this would indicate that you made some difference. Okay, so how do we do that? First of all, we want paired t-tests because the scores belong to the same teacher. This is why we're measuring using a dependent test. What we're doing is ultimately we're measuring a difference in these means to see if there is a difference. And because they're the same person, the pre-test and the post-test are taken by the same person, they're dependent upon each other, okay? So you can see how we've pulled these three different terms in here: a dependent, a correlated, or a paired t-test. They all mean the same thing, and you can see why that is the case. So the way we do this then is in Excel, when you put your data in, you go into data, and you should have a data analysis toolpack. If you don't have a data analysis toolpack over here, you can go into options, scroll down to options real fast, and under add-ins you can see here's the data analysis toolpack, and you would highlight it and click OK. But since I already have it, so we're just going to click on this, and so here is our data analysis toolpack, and you can see we have a lot of things that have already come up in our class that we have spoken about, and other things that we will talk about before our class is over. So we're doing a t-test. We said there are 3 t-tests, and we want a t-test paired to sample for means. And what that means is a dependent t-test or a paired t-test. So we click on that, click OK. It's wanting us to input our range. So our first variable then we would just highlight. In our second variable, I've already done this, but we would highlight all of those as well. Our hypothesized mean difference is 0. Our null hypothesis is that they are equal. I did not include the labels. If you had included the labels in your first cell as you went down, you would indicate that you included the labels. Our alpha, this is our level of significance. We want it set at 0.05. And the last thing then on here is the output range. So the output range is where you want your chart to show. So I'm just going to highlight output range there where it's blinking. I'm going to put it here. Okay, and then we just hit OK. So now we have our results. So what are our results showing here? So we have a lot of stuff in here that doesn't necessarily apply to us, but you can see some things that we have covered in the past. There are the means for the 2 variables, the pre and post test. There are the variances for the 2 variables, our observations for the 2 variables. Our degrees of freedom for a dependent test is n-1. And so our degrees of freedom here is 15. This is an important number. This is our t-stat. This is our t-value that we calculated. And so it's 3.8559. So it's a pretty significant t-value. So we can probably guess it's going to be significant. But the great thing about Excel is it tells us what our critical value is for t at a 2-tailed level. And we would want a 2-tailed test here. While we anticipate that improvement would be made, we want to see if there's a difference either way. So we would do a 2-tailed test. So you can see here, and there's the critical value for 1-tailed. So you can see here the 2-tailed critical value is 2.13. Our t-value is 3.86. So we would reject our null hypothesis. So let's go back to the PowerPoint. And this was the slide where we left, where we looked at the formula. So let's move to the next page. So this is what we had here on the Excel. Okay, and you can see what we said. Our 2-tailed critical value was 2.13. We had 3.85. So we would reject our null hypothesis that our means were the same, and accept our alternative hypothesis that the training had a positive impact on the self-efficacy of non-reading teachers teaching reading. Okay, so I've done a similar test like this. That's why I use this example a lot. So that's the example of a dependent t-test, and you can probably think of things that you could use with your students. The best one here would be a pre-post test that you would give them to see if there's some significance. So then our next test is the independent test. Okay, and we have two versions of the independent test, the pooled variance and the separate variance. And so that's what we need to examine now is which one do we want to use, the pooled variance or the separate variance. So let's suppose you want to measure the impact a program has on two groups of students. You want to see if there's a difference on ACT scores after an intense study program. So you have a control group who receives no study prep program. And of course you have an experimental group who receives an intense study program. So we have two separate groups. Unlike before where we had just the teachers taking two assessments, now we have two separate groups. Okay? Both groups will take the ACT in 2 months, and you want to see if there's a difference in the ACT scores of the two groups. So remember our flow chart. So let's start back at the top. Are the scores for the two means from the same people? No, this time they are not. Are the same number of people in the two groups? Well, we didn't get that far yet. But for the sake of this, we're going to say yes. Okay, and we'll see later what to do if they're different. Okay, if they're different, we're going to have to consider using the separate variance. But for the sake of this, we're going to say yes. So now we can go over here to the green table and do an independent t-test for a pooled variance. But just because we have the same number of people, we need to have our variance as equal. Okay, and so let's go to the next slide. Really, it should change slightly here. Are the variances of the two groups? If we say yes, that we have the same number of people, it's not automatically there. Now we're going to go down and ask about the variance in the two groups. So what we're looking for now is called homogeneity of variance. Okay. Homogeneity just simply means difference. So we want to see if we have a significant difference in our variance. And we know what variance is. It has to do with the difference in the deviation around the means. And we simply take the square root of our variance to get our standard deviation. But we have some specific rules dealing with variance. Okay, so we've determined that there are two groups of people, so we need to do an independent test. But now we have to ask two questions. Are the numbers of people in the groups the same or not? And is the variance in the two groups the same or not? And so, if the variances are not equal, and the sample sizes are not equal, then we use what's called the separate variance model. Okay, we're going to explain both of these. If the variances are equal, then we can use the pooled variance model. And then finally, the last one, if the variances are unequal but the sizes are the same, then we can use either model. Okay. So how do you know if the variances are equal? We can determine the variances, but just like everything else that we've spoken about, we're taking samples and we know that they're not going to be exactly the same. So we have to have some kind of a test to see how much difference we can have between the two variances to determine whether or not they're equal. Well, believe it or not, there is a test in statistics that does this. And that's what we're going to look at. It's called an F-test. It's very simple. We're going to do a lot more with the F-test in the next module, but for now, We're going to use it to test variance. Let's say that our null hypothesis is that the variance of group A is equal to the variance of group B. Okay, that's typically what we say the null hypothesis is that they're equal. Here we're testing for homogeneity, the differences among the variances, and so our null hypothesis is going to be there is no difference. If we reject it or fail to accept it, as we will see, then we would say there is a difference. So let's test it. Okay, it's simply called an F statistic. You simply take the larger variance and divide it by the smaller one. Okay, so let's say our variance in group A is 2.13 and our variance in group B is 3.71. We do the math, 3.71 over 2.13, and we come out with 1.74. Now, we have 7 students in each of these groups, these imaginary groups that we're using here. Okay, so our students are equal. Now we're testing to see whether our variance is equal. So we divide the larger by the smaller, and we get an F value of 1.74, and our degrees of freedom, we know we have 7 students in each group. Okay, so what we would do then is go to our F value chart. Okay, and I've highlighted here, this is a little bit different chart. So the top row is at the 0.05 level. The bottom row is at the 0.01 level. We're doing at the 0.05, so we're only looking at the top row. The way we determine which intersection we want to look at is we look at the degrees of freedom in our numerators and the degrees of freedom in our denominators. Okay, so this particular one had 7 in each group, so it didn't matter which is which. We had 7 in each group, so we go 7 in our numerator and we go down to 7 in our denominator, and we come across here as a critical value of 3.79. Our F value is 1.74. So the fact that our F value did not exceed our critical value of 3.79 means that we failed to reject our null hypothesis. Or, I'm sorry, means that we cannot reject our null hypothesis. We're going to get into terminology later, but basically for now just assume that we're going to accept our null hypothesis. We failed to reject it, so we're going to accept it, which means that the variances are equal. So even though they look different, they're still within the range, and we're going to say that they're equal. So going back to our rules, if the population variances are not equal and the sample sizes are unequal, use a separate variance model. No, we just determined, number 1, that our sample sizes are equal, they both have 7, and number 2, that our variances are equal. So we cannot use the separate variance model. Number 2, if the variances are equal, use the pooled variance model. And that's what we're going to do. We're going to use the pooled variance model because they're equal. All right, so let's just reiterate what we're looking at. We're looking to see if we had 2 groups of students, control group and experimental group. The control group did no study program. The experimental group received some intense study program on their ACT, and then 2 months after that, or during a 2-month period, and then after that, both groups took the ACT test. And we want to see, is there a significant difference between the 2 groups based on their ACT scores? So we're going to go to the Excel sheet, but I want to show you the formula. So it's a little bit different than our other formula. Number 1, notice, again, we have our means at the top. We have square root at the bottom. But notice we've changed it slightly here. One thing we've changed is our degrees of freedom. In the dependent test, our degrees of freedom was n minus 1. Here, since we have 2 groups, we have to have, we're going to add them together and subtract 2, 1 degree of freedom for each group. Okay. So let's take a pause here and let's go to Excel, and I'm going to show you how to do this in Excel. Okay, we're back in Excel, and you can see here are the ACT scores for the students who received the Intense program. Actually, I think I have 8 on here, but it doesn't matter. And the ACT scores for the students who did not. So here are the variances. Just to show you our F-test, we came out with 1.74. Our critical value was 3.79. So how do we do this in Excel? So again, we go to Data. We go to our Data Analysis tool. This time, we're going to do a t-test for 2 samples, assuming equal variance. Okay. And so again, what we're going to do is we're going to input our range 1, our range 2, our hypothesized mean difference is 0, so we're going to leave that the same. I did not include labels. Our alpha is at 0.05, and our output we're going to put right here. And so when we click enter, so what we're seeing now, number 1, again, there are our means, the variances for each, the number of observations we have, our pooled variance, our hypothesized mean difference we said would be 0, our degrees of freedom was 14 because we had a total of 8. So here are our important numbers. Our calculated value of t is 3.365, and our critical value of t for a two-tail test at the 0.05 level was 2.14. So since our t-stat, our t-value exceeded our critical value, we would reject our null hypothesis that the means were the same and accept our alternative hypothesis that the Intense program did have a significant impact on ACT scores. So let's go back to our PowerPoint now and look at that. So this is the slide where we left off, and just to show you, this is where we get our pooled variance. Okay, the formula over here on the left in the square root. So here's what we showed. Again, because our t-stat exceeded our two-tailed critical value, we would reject our null hypothesis and accept our alternative. Okay, so that's a pooled variance. We had the same number of people, and our variance was considered to be equal. So the last test then is what we call our independent t-test of unequal variances. Okay, so let me give you an example of this. Let's say you have 2 teachers teaching the same subject. They have very different approaches, and you want to determine if one approach promotes student learning better than the other. Okay, so let's see what we have here. We have Class A that uses traditional textbooks, you can say lecture format kind of thing. And Class B uses online textbooks that incorporate videos and all kinds of fun things that go with them. So we can determine, let's say we have determined that the average for Class B on the district-created final exam, and we're going to assume that the final exam is a reliable, valid instrument. The average for Class B was 84.39. In Class A, the average was 80.67. Okay? So, the question is, do we purchase the online textbook? Here's that thing we've been talking about. On the surface, yes, it looks like we do, but we need to look at statistics and see if there's actually a statistical difference between the 2 groups. So we can go to our Excel sheet. So let me show you first of all the formula for the separate variance. Okay, so it's very similar, but notice we don't have 2 areas down here where we had our pooled variance earlier, we're just adding our variances together and, after dividing by the n of each group and then taking the square root of that. Okay? So let's pause this and go to Excel. So here we are back in Excel, and we can see that Class A, which used the traditional class teaching method, had 9 students in it. Class B, which used the online textbook, had 14 students in it. Okay, or 13 students in it actually. So the populations were unequal. When we looked at the variances, we see the Class B averages here I highlighted in yellow. When we looked at the variances when we did our F-test for variance, dividing the larger by the smaller, we saw that it was actually significant at 2.74. Our F critical was 2.72. So our variances are not equal. So we have an unequal sample size and we have unequal variances. And so because we have unequal variances, we're going to use the independent separate variance test. Okay. So again, we simply go to Data, go to our Analysis Toolpack, and this time we're doing a t-test to sample assuming unequal variances. And again, we simply input our data. So notice we're highlighting differences in them. So we're just highlighting the scores. It will figure out that they're different. Our hypothesized mean difference is 0. We're not including labels, alpha at 0.05, and we want to put our table right there. So let's hit OK. Let's spread this out and see what we get. So our mean, again, we saw that already, that our mean score in Class B that used the technology was higher by 2.5 points. There are variances. There are the observations. Our degrees of freedom here was 12. Notice our t-stat, or our t-value we have come up with, is minus 0.6563. Our two-tailed critical value is 2.17. It did not exceed our t-stat did not exceed our critical value. So therefore we cannot reject our null hypothesis. And so what we're going to do is we're going to say we failed to reject it. And up until this time we've been saying we accept our null hypothesis. But I want to start shifting you in a different direction and say we failed to reject our null hypothesis, and I'll explain that to you in just a second. So let's go back to the PowerPoint. So this is where we left off, and when we pull our data in, so this is what we saw. So even though the averages are higher for Class B, the test reveals a t-score of negative 0.6563, a critical value of t at 2.1788. Because our t-value is below the critical value, it did not exceed it, we failed to reject our null hypothesis that Class A equals Class B, and we do not purchase the program. Okay, so we failed to reject that. So if anything, if we're wrong, we have committed a type 2 error, which means that it could have made a difference in the students' scores, but we didn't see a significance, and we didn't expend any extra money, and things remain the way they are, the status quo. Okay, that's a type 2 error. We failed to reject our null hypothesis when we should have. So I told you that we need to start training ourselves to saying fail to reject as opposed to accept. Okay, so notice we did not accept our null hypothesis. Technically, if we accepted our null hypothesis, what we would be saying is that the difference we saw is completely random. Okay, if we accept our null hypothesis that A equals B, then we're saying the difference is completely random and it's a closed case. But if we say we fail to reject the null hypothesis, that means that under the conditions in which we measured the two variables, we did not see a significant difference, but there may be other things out there that we did not consider. Okay, so as opposed to saying, and this is again a matter of semantics, but as opposed to saying we accept that there is no difference, when we say we fail to reject it, what we're saying is that we're saying we still believe somewhere in our minds that the alternative hypothesis may be true under different circumstances. Because keep in mind, the alternative hypothesis is typically what you want to be the reality. Okay? And so we're just not shutting the door on further study of something when we say we fail to reject, as opposed to if we accept our null hypothesis that they're the same, then we have closed the door and it's done. Okay, so just a matter of semantics there, but some technical stuff for you. So again, we're not going to use the actual formulas anymore. We will be doing these things in Excel. The Excel sheets will be provided in Google, or not Google, in the module so you can see them. Let's quickly review our module goals that we had for this. We wanted to describe similarities and differences between distributions in the normal curve. And we were talking about the fact that this all depends on degrees of freedom. And that as our degrees of freedom changed, so did our critical values, where we were used to seeing a critical value at the 0.05 level of 1.96. That was for the normal curve using z-scores, but under t-distribution, that's a moving target depending on the number of degrees of freedom we have. Distinguish between the correlated, the dependent, or paired tests, all those mean the same thing, and the independent t-test models. And this has to do with the dependent test. If you're looking at one group using assessments as opposed to two groups, it's maybe same size, maybe different size, maybe equal variance, maybe not equal variance. Those are the independent tests. Perform the necessary procedural tasks for determine whether to use separate variance or a pooled variance test, t-test model. That was our f-test that we used, dividing the larger variance by the smaller one. Compute the degrees of freedom for the three test formulas discussed. Calculate t-values using an appropriate t-test model when provided. We didn't actually calculate them. Now we use Excel to do that for us. Use the table of t-values to determine the critical value of t for the areas of rejection. Again, we don't necessarily do that anymore now that we have Excel and other programs that do that for us. Interpret the test of the null hypothesis from a t-test. And then finally discuss the non-significant results in an appropriate manner. And that was really getting at that idea of that we need to start saying we failed to reject, which will leave open the possibility that in the future we might find different conditions where things are very similar. So that's the introduction to t-tests and all that goes with them. We will work over this a little bit with some basic stuff and then getting into choosing which t-test you want to use and putting them into Excel. So with that, as always, if you have any questions, please feel free to reach out and get in touch with me.